Mathematics research is messy, iterative, and deeply human. Beneath every polished proof lies weeks of failed attempts, half-formed conjectures, literature hunts, and computational experiments. Today, we're looking at a new system designed to support that full, messy reality, the AI co-mathematician, a workbench that lets researchers interactively leverage AI agents to pursue open-ended mathematical discovery. The problem the AI co-mathematician is trying to solve is one of orchestration. We already have powerful AI tools for theorem proving, evolutionary search, and conversational problem solving. But standard chat interfaces are transient. They forget context, can't manage branching hypotheses over days or weeks, and force the mathematician to manually connect all the pieces. Software engineers solved this with AI coding environments. Mathematics has nothing equivalent. Until now, the design of the AI co-mathematician is grounded in 7 core principles drawn from the history of mathematical practice. The system embraces mathematics beyond proofs, supporting literature search, brainstorming, and numerical experimentation. It supports iterative refinement of intent, because in mathematics, formulating the right question is often harder than answering it. And it produces native mathematical artifacts, living working papers rather than transient chat logs. Here's how the system is organized under the hood. Rather than a single chatbot, the AI co-mathematician is a hierarchy of specialized agents sharing a common workspace. A top-level project coordinator agent communicates with the user and delegates work downward to workstream coordinator agents. Those agents in turn dispatch specialized sub-agents for tasks like literature search, deep reasoning, or writing and executing code. All agents share a file system and communicate through an internal messaging system. Let's walk through a real session. A mathematician wants to prove upper bounds on a variant of the moving sofa problem. How large a sofa can navigate both left and right-handed right-angle corners. Instead of immediately generating a solution, the project coordinator opens a dialogue. It reads an uploaded paper, identifies which subproblems are still open, and asks the user to clarify their focus. Once the user approves a set of goals, the system moves forward, ensuring all downstream effort targets the researcher's actual intent. With goals approved, the system branches into parallel workstreams, one per goal. Each workstream is managed by its own coordinator agent and runs asynchronously, so heavy computation doesn't block the user. Here you can see the workspace view. Each goal has one or more workstreams attached, each producing incremental reports the user can read while work is ongoing. If a workstream fails, a prominent warning is displayed rather than silently restarting. Inside a single workstream, the coordinator agent takes a linear sequence of actions, searching literature, running code, querying the web, and updates the user-facing report after each step. When the report is ready, it goes through a formal review process with dedicated reviewer agents who check logical correctness, cross-reference citations, and validate code outputs. Only when all reviewers formally approve is the workstream marked complete. One of the most important features is how the system handles failure. When a computational search blows up in the SOFA problem session, the coding agent cannot mark its work complete until tests pass and a reviewer accepts it. Rather than silently looping, the system surfaces the blockage to the user with a specific message asking for help. The user responds with a topological pruning heuristic and steers the system to open new bounding strategy workstreams, all while other work continues in parallel. Let's look at real results from early users. Mark Lackenby, a mathematician at Oxford, used the AI co-mathematician to resolve an open problem from the Korofka notebook, a long-standing question about whether every finite group admits a just finite presentation. The system produced a proof strategy that its own reviewer flagged as flawed. But Lackenby read the flawed draft, saw a clever core idea, and recognized from the reviewer's critique exactly how to fill the gap. Human and AI together completed the proof. In a second case study, Gergely-Bertsy investigated conjectures about Stirling coefficients for symmetric power representations, specifically that certain coefficients are strictly positive and form a log-concave sequence. He uploaded a rich background document, a style he called structured posing of questions. The system established proofs for 2 conjectures in separate workstreams, each with full computational evidence. Crucially, A marginal annotation in the output document flagged a key insight that Berchi then explored further through the chat interface. Now let's look at benchmark performance. On an internal set of 100 research-level mathematics problems with code-checkable answers, the AI co-mathematician significantly outperforms both Gemini 3.1 Pro and Gemini 3.1 Deep Think as standalone models. The bar chart here tells the story clearly. The system succeeds where base models fail because it can write and test complex code libraries, retrieve precise theorem statements from literature, and catch its own logical errors through the iterative review cycle. On the external Frontier Math Tier 4 benchmark, 50 problems described as short-term research projects by professors and postdocs, some potentially unsolvable by AI for decades. The AI co-mathematician achieved a new high score of 48%, correctly solving 23 out of 48 problems when the two public samples are excluded. The evaluation was conducted blind by Epoch AI. Notably, the system solved 3 problems no prior AI system had solved, while the underlying base model, Gemini 3.1 Pro, scored only 19%. The system is not without limitations. The iterative review cycle can sometimes converge on a subtly wrong argument that neither the AI agents nor a casual human reader catches, a reviewer-pleasing bias. Conversely, agents can get stuck in endless revision cycles, degrading into what users call a death spiral. There's also a fundamental tension. The longer the system runs autonomously, the more it can accomplish, but the more opportunities arise for it to go off track without human correction. The AI co-mathematician represents a new paradigm, not an oracle that answers questions in isolation, but a stateful collaborative workspace that mirrors how mathematicians actually work. It captures failed hypotheses, synthesizes literature, manages uncertainty explicitly, and produces living working papers, all while keeping the human researcher firmly in the loop to steer, correct, and ultimately make the discoveries. The next revolution in AI-assisted mathematics won't just be about solving problems faster. It will be about helping researchers navigate the unknown together.